Hello everybody. The topic of this video is time dilation in special relativity. First we'll deal with the definition of time dilation. What is time dilation? Time dilation is the effect by which two observers in relative motion measure each other's time to have dilated or elongated. That is, two observers, when they are in relative motion, if they measure any process related to time of the other observer, he would find that that particular process has elongated or time itself has slowed down for the other observer. Now here we have listed two different types of time dilation. First one is kinematic time dilation, which is explained by the special theory of relativity. The second type of time dilation is gravitational time dilation, which is explained by the general theory of relativity of Albert Einstein. So these two are different effects. So you could have time dilation due to motion of objects. You could have time dilation due to the gravitational field present near a massive object. So these two are two different time dilation effects. First, let us briefly discuss about this one, because the topic of this video is kinematic time dilation, because we have given the title as time dilation in special relativity. So the first one is the video's concern now. This one will just briefly define what it is. So an observer near a massive object with a strong gravitational field would find his clock to be running slow compared to how his clock would run if he is farther away from the massive object. So near a strong gravitational field, clocks would run slow. That means time would dilate. So such a time dilation is called as gravitational time dilation, and that is explained by the general theory of relativity. That is not going to be discussed in more detail in this video. In this video, rather, we will focus on what is called as kinematic time dilation. That is, two observers in relative motion to each other would measure each other's time to have dilated compared to his own or her own time. That is, observers, when they carry clocks with them, if they are measuring their clock and comparing the time, same time measured in the other person's clock, he would find that time is running slower for the other person or the other observer in relative motion with respect to himself. This process is called as kinematic time dilation. So let us briefly understand this further with an example. Let us say there is an observer O who is stationary on Earth, and he has a clock. Now let us say he measures a certain event to take a duration of time, let us say T0, in this clock. If the same observer O compares, let us say, his measurement with another observer who is traveling, let us say, on a spaceship carrying another clock, let us call this observer as O prime. The same event he would measure in this clock, that is, observer O would measure the same event to have taken a different time as reported by this clock C prime, carried by this person who is traveling with a velocity v with respect to this observer who is on the Earth at rest. So this Earth based observer is at rest. His clock is reporting a time T0 for a certain event. For the same event, the traveling observer, his clock would measure a time T which is different from T0. Now what is the expression that connects these two time durations? T is equal to T naught divided by square root of 1 minus V squared by C squared. Such a simple looking expression connects these two time durations measured by this observer O. Please so remember, both the times are measured by this observer O, who is at rest on the earth, and with respect to him this observer is moving with a velocity V. So both times are measured by the same observer. This is very important to note. Now this T naught that he measures in his own frame of reference is called as proper time, and on the other hand the other time that he measures is the dilated time, because it is going to be greater than this T naught. So this time is a longer duration of time, so it's a dilated time. How? We know that special theory of relativity, the two postulates that we discussed in our introduction to special theory of relativity video, we know that nothing can exceed the speed of light according to the postulates of relativity. So V can never be greater than C, so V is always less than C. That means this term is going to be less than 1, the denominator, and then if it's a fraction, then you know that it is in the denominator, so the left side has got to be greater than the right hand side, so you will have T always greater than T naught. So now whenever an observer in motion, his clock is measured by an observer who is at rest with respect to the observer in motion, he would find that the other person's time has dilated. Right, so we are talking about a time measured by the same observer in this case, and this is the very important expression, the time dilation expression given by the special theory of relativity for kinematic time dilation. We are not discussing the expressions for gravitational time dilation in this video. We are not going to discuss this in detail, but this is the kinematic time dilation. Now we have to understand the origin of this expression. We know that there are different ways one can arrive at this expression. One can derive this expression in different ways. I will try to derive it in a very simple way. We will have to do the derivation now. Okay, now we will try to derive the expression for time dilation using a simple thought experiment. In this thought experiment, we have two observers, observer O and observer O prime. Observer O is at rest on the earth, whereas observer O prime is traveling at a velocity V with respect to the observer O. Now both the observers should have some way of measuring time. There is a simple setup here. There is a source of light which also acts as a detector, D, and there is a mirror. Now a light beam is sent from the source of light and goes a distance L0 to reach the mirror, and then gets reflected back to the source where it is detected. Once the light beam has been detected by this detector, again the source will be triggered to send the next beam of light. So this is like a clock ticking with a constant time interval of T naught. This T naught is the time duration, and the speed of light is c. So velocity is distance over time. So we want time, so it is total distance over velocity c. So 2L0 by c is the time duration for the light beam to go back and come. So L0, another L0, L0 to reach the mirror, and L0 to get back to the source again. So after reflection, it has traveled the total distance of 2L0, and the 2L0 over the velocity c is going to be what? Duration of travel for this beam. So this is the time that is measured by this observer O. Now suppose this observer is moving carrying an identical clock. For him, he would measure something similar, that is for the observer O prime, he would measure something similar in his frame of reference because he is traveling with the clock. But for this observer O, if he tries to measure the event from his frame of reference, he would find that since the other observer O prime is moving with respect to him, he would find that when the light beam is emitted by the source, it starts going in this direction because it is moving in this direction with a velocity v. So by the time it reaches the mirror, instead of going perpendicular to the direction of motion, it would go in a diagonal direction and reach the mirror at this point for this observer. So this observer would find that it has gone like this, and it has traveled a different distance L now, not L naught. From his frame of reference, he would see that it has gone like this. After reflection, by the time it reaches back to the source, it would have traveled another L in this way. So this would be the observation of observer O of the event that is happening in the frame of reference of observer O prime. But the observer O prime who is traveling with this particular clock would measure something similar to what observer O would measure in his frame of reference, but what observer O would measure of observer O prime is this scenario. Now you can see that the distances are different. Here we can simply use the Pythagoras theorem and we can try to calculate L. L is nothing but this distance is again L naught. If this particular event has taken a time t as measured by observer O, the velocity is v. So the distance that this particular clock has moved from this point to this point, that distance would be v times t, and this time is according to observer O of this particular time taken by this beam to travel from the source to back to the detector. Right. Now we can write a simple expression for this L and then try to derive the final result for time dilation as measured by O. So we can write L as being equal to square root of L naught square plus this is half Vt. The entire thing is Vt, so this is going to be half Vt. So you have square of that, so 1 by 4 V squared T squared. So this would be the distance traveled by the light beam from the mirror, from the source to the mirror as measured by observer O. Right. So we have these expressions now. We can now square this one on both sides. So we have L squared on one side. Here it is going to be L naught squared plus 1/4 of V squared T squared. Now from this expression we can say that L is half Ct, so L squared is 1/4 C squared T squared, 1 by 4 multiplied by C squared T squared, and L naught square is 1/4 of the same way. This is going to be 1/4 of C squared T naught squared plus you have already another 1/4 of V squared T squared here. So now what is common here? 1/4 gets cancelled everywhere, and then we'll try to now combine these two terms. Both have V C squared T squared, V squared T squared, so T squared can be combined here. So we'll write the next step as C squared minus V squared multiplied by T squared, which is a common factor, and on the right hand side you still have C squared T naught squared. Now dividing the whole expression by c squared, we would get c squared over c squared is 1 minus v squared over c squared t squared is equal to t naught squared. Now we can continue here. Therefore, t is equal to t naught over square root of 1 minus v squared by c squared. So this is the time duration measured by the observer O in his own frame reference, in his own frame of reference, and this is the time duration that he measures in his own frame of reference, that he measures in his own frame of reference of the other observer, that is observer O prime. So this is the dilated time and this is the proper time. So your dilation is given by, time dilation is given by this expression. So this is a simple derivation of the expression for time dilation in special theory of relativity. This time dilation is of course also called as the kinematic time dilation. Now there are elegant ways of writing this one, commonly used in special relativity, that is the fraction v over c is denoted by the symbol beta, and this thing 1 over square root of 1 minus v squared over c squared is gamma. Of course this has a special name. This is called as the Lorentz factor. So one can write the same expression t as t naught gamma times t naught, rather, because gamma is 1 over 1 minus this thing, or t is also equal to t naught 1 minus beta squared. So these are the different ways in which you can write the expressions for kinematic time dilation. Now there is some interesting question that should come up. We have talked about in our example two observers, observer O and observer O prime. Now observer O measures the duration of certain event that is happening in his frame of reference as t naught, and the same event if he measures from the clock of the observer O prime, which is traveling at a speed v, he measures that to be equal to t is equal to gamma times t naught. Now the question is, what about the observer O prime's measurement? That means my question is there some kind of symmetry between the measurements of O and O prime? That is, if O prime tries to measure the clock of O, because he is also in relative motion with respect to O, so if he tries to measure according to his frame of reference, O is in motion in the opposite direction with the same velocity. So he should also be able to measure the clock of O to have slowed. Does it happen is the question. That means the question is very simple here. Is kinematic time dilation reciprocal? So the question here is kinematic time dilation reciprocal? Yes, it is. A resounding yes. Very important point that one has to consider when talking about time dilation. It is mutual. it is symmetric about the two frames of reference. That is, as O measures his time to be proper time and the other time to be dilated time, O prime also would measure his time to be proper time and the other time to be a dilated time. So the time dilation is reciprocal. Now this brings us to the famous twin paradox of special relativity. Twin paradox. What is twin paradox? So twin paradox is a famous experiment in relativity, that is a thought experiment where we have twins, let us say Ram and Shyam. They try to do an experiment, thought experiment, in which Ram stays on Earth and Shyam flies to a distant planet on a spaceship at velocity v, and v should be generally very high, I mean space travel, so we know that it should be at relativistic speeds. Now Shyam reaches the planet, it takes several years and then he comes back. Now according to Ram, the clock carried by Shyam should have dilated. That is, time should have dilated for Shyam but not for Ram. And when Shyam comes and verifies the clock held by Ram, he will find that this clock should have dilated according to him, because we just now mentioned that the dilation is reciprocal. So both should measure each other's time to have dilated. But in reality, if this kind of a travel happens, though this is a thought experiment, one can imagine such a thing to happen maybe in distant future. If such a thing happens, you would find that only Shyam is actually younger, because Shyam traveled and this guy Ram stayed back on Earth, so Shyam would definitely be younger. Both are twins, so remember that we know that time dilation is reciprocal, so we would expect that both should have aged equally according to each other, but that's not the case. When such a thing happens, definitely you would find Shyam to be younger than Ram. We know that it is reciprocal, but still this is happening, and there are reasons for that, and that can be actually answered not just with special relativistic ideas. We need to understand a bit of general relativity to solve this paradox. So there is actually no paradox, because there is a symmetry in the measurements. Each other's clocks are measured by the other, and each one's clock is measured by the other. Therefore each would find the other clock to have slowed down, so there is no paradox. But there is, in reality, you would find that Shyam would be younger than Ram, and that is because of some reasons that we cannot discuss in this video. So we separate video would be posted on twin paradox. Please do check out that video as well. Finally, there will be a question: are there any proofs for time dilation or other relativistic effects? Are there any tests for time dilation specifically? Yes. Several experiments have time and again proved both special relativity as well as general relativity. In particular, are there any tests for time dilation? Yes, there are several experiments, but one direct experiment is due to Hafele-Keating, a physicist and an astronomer. Together they performed a flight experiment where they carried 4 cesium atomic clocks aboard international flights, commercial airlines, in 1971, trying to measure experimentally how much time dilation for the flight travel. For this experiment, they performed around the world travel in 2 directions. eastwards and westwards, because they expected to find a small difference between the time dilation for eastward and westward motion because of Earth's rotation. And they indeed found time dilation both due to special relativity as well as general relativity. That is, they found kinematic time dilation as well as gravitational time dilation effects in their experiment, a very important direct experiment measuring time dilation. So there are several tests that have proved time dilation to be true. Thank you.